Hi, my name is Hayden Coffing, and I'll be presenting this paper, Self-Supervision is All You Need for Solving the Rubik's Cube by Kayo Takano. So, solving the Rubik's Cube is hard. If you ever tried it, it's pretty hard. It's because there's 10 to the 40 arrangements, and exactly one of them is solved. Additionally, you can do many different moves to get to the same state, like moving it this way is the same as moving back 3 times. So the problem is actually NP complete and is called a combinatorial search problem. Another combinatorial search problem is like the traveling salesman problem. And unlike the traveling salesman problem, it has exactly one solved state. So generally we used heuristic algorithms to solve these combinatorial search problems, but that led to the exponential time and factorial time algorithms, which is no good. So we started training neural networks on these combinatorial search problems, and it led to a lot faster run times. That was done by Applegate in 2011. When it pertaining to the Rubik's Cube, we can transform it to a graph theory problem and then use the similar algorithm to the traveling salesman problem to get a faster solver. That was done by Korf in 1997. So here's the graph that we're going to transform the cube into. For each state of the cube, which is like the scramble, all outgoing edges are just corresponding to a certain move. So then we can train the neural network from going from any solved state to any given scramble, which is just like a messed up cube. And then if we can go from any solved state to any given scramble, we can take any given scramble, reverse all the moves we got to get there to get the solved state back. So that's how we're actually going to solve the problem. So we're going to go over some prior work real quick. So this Korf guy, he used a iterative A-star search on the graph, the graph presented in the last slide. That was very slow. And then came these IDA star solvers by those people. And it led better results on the Rubik's Cube, but it lacked generality. These IDA star solvers use graph theory and a lot of other group theory and a lot of other advanced math to solve it. More pertinently, there's this Deep Cube A by Agnostinelli in 2019. So his net use a far less nodes in the cube tree, like that graph before, by having a large graph with fewer nodes and being able to transform some different solution into one of these other nodes. You can go backwards and solve the cube. So the solution that Kayo is presenting here uses a lot less nodes, and it uses a wider beam search, which is kind of like a breadth-first search, and has a slightly different architecture than the Deep Cube A solver. So the neural net consists of 2 linear layers, one 5,000 dimensions and one 1,000 dimensions, followed by 4 residual blocks containing 2 1,000 dimensional linear layers and ReLU activation, and then batch normalization after each linear layer. Finally, the neural network has a 12-dimensional layer that returns logits as an output, which is basically like a move that is then transformed into a probability distribution using the softmax function. And then over there is the algorithm to train the net. So the data that this neural network was trained on is the same as the Deep Cube A solver. It has 1,000 Rubik's Cubes test data, where each cube is scrambled with 1,000 to 10,000 moves, which is kind of weird because Gauss number, which is the number of moves to solve any cube state, is 20 if you count one move as like 2 turns, or 26 if you count one turn, like 2 turns as 2 turns. That's a pretty normal way to count the amount of turns on a Rubik's Cube. Turns out this state right here, it's called the super flip, is the hardest state to solve. It takes 26 moves to solve it, therefore God's number is 26 in quarter turn metric. So the neural network was trained to predict the next move in a random scramble. It used an atom solver with the maximum scramble length of 26 and the learning rate of 10 to the negative 3. So it had 2 million steps in each training with batch size of 26,000 for a total of 2 billion solutions, which sounds like a lot, but when compared to the solved tree, isn't a whole lot. So the results. It turns out that the proposed solution isn't entirely optimal, but it is faster than DeepCube. There are discussed previously, the IDA star solvers are a little bit faster and lead to shorter moves. But the real killer feature of this approach is that it can be generalized to not just Rubik's Cubes, but any combinatorial search problem with exactly one solved state. You might think of like one of those 15 sliding puzzles. It was on the Mac background for a little while. You can like slide it around. Or the game Lights Out is another combinatorial search problem with one solved state. So the solver trades off optimality for generality, so it can solve cubes and other combinatorial search problems. Still a little bit slower, but it only is off by one move, which is really surprising. And it's a lot faster than the prior art and yields better results. You can see that it runs a lot faster and converges to optimal solutions much quicker. And that is it.